Hello and welcome. Today we're going to be talking about Faraday's law. This is a new piece of physics that we haven't had before. We're going to discover a new way of actually making fields that isn't associated with stationary point charges. We're going to find that these fields are just like every other kind of electric field. They exert forces on charged particles and whatnot. And we're going to explore how we can quantify this to come up with Faraday's law, which is the third of Maxwell's equations. So we're talking about sources of fields. We have field, what it affects, and what the sources are. And we've talked about two different kinds of fields. So we have electric fields. It affects a charge, some other charge. And the source is, so charge Q2, the source is some charge Q1, which can be stationary or moving slowly. We've also talked about magnetic fields, which are made by moving charges, affect moving charges. So, and the source is some moving charge. But it turns out that there is another way to make an electric field. There's another possible source for an electric field. And it turns out that a time-varying magnetic field can be the source of an electric field. So I'm going to share my screen with you and show you a video that's a demonstration of Faraday's law. What you're going to see is a coil. Actually, it's a solenoid. It's kind of a long coil. It's connected to an ammeter. This is an old style ammeter called a galvanometer. It's got a needle that can deflect one direction or the other depending on whether the current is going one way or the other. And what the demonstrator is going to do is take a magnet on a stick just so he can hold it and insert the magnet into the coil and then pull it out. And you'll see that during part of that process, and watch carefully to see whether you get a current when the magnet is stationary or when it's moving. So watch carefully, and you'll see that during part of that process, there's actually a current through the coil that registers on the ammeter, even though the coil is not connected to a battery or a power supply. So this is a very new phenomenon. So let me share my screen. Okay, so here is a demonstration of Faraday's law.
And today I want to demonstrate Faraday's law and give you a bit of an explanation as well. So in front of me I have a coil, and that is connected to this ammeter or galvanometer. And I also have a rare earth magnet, and this magnet is facing so that the north is facing outward like so. What's going to happen when I insert this magnet into this coil? You see the needle deflect. What if I do this faster? You should see that the needle deflects a greater amount. So what's going on?
Okay, so if you watch carefully, you saw that when the magnet was moving fast, there was a large current through the coil, which means that there was an electric field around the wrappings of the wire in the coil. When the magnet was moving slowly, there was a smaller current. And when the magnet was stationary, there was no current at all. So our job is to explain what's happening. Okay, so what we saw was when the magnet was moving inside the coil, we actually got, you saw a current, and if you moved the magnet faster in the coil, we saw a bigger current. So therefore, it seems like the, if we have but when he held it still, there wasn't any current. So if we have a magnetic field that's changing with time, there could be a current in the coil. And if there's no time varying magnetic field, then there's no current. So let's look at a VPython program that actually relates to this. Okay, so here we've got a magnet. The red end is north end. It's going to move and the magnetic field changes everywhere in space. Where we're interested in the magnetic field, though, is around this loop here, or rather on a surface that's stretched across a loop that we're drawing in space. So we're drawing another of these mathematical surfaces, but what we've got is we're interested in the outside of the loop, but we're also interested in what's going on inside the loop. And so as we move the magnet, we can see that the magnetic field inside the surface, and here it's only drawn along one line, but of course it's going to fill this entire surface here. We're just drawing one line so we can see what's happening. So the magnetic field increases and decreases as the magnet moves. And we see around the edge of this loop an electric field. So the cyan arrows are magnetic field and the orange arrows are electric field. And we can see that as the magnet moves, and what must be really the magnetic flux through this surface changes. On the edge of our loop, there's an electric field that changes in magnitude and direction, depending on the direction of change of the magnetic field of the magnet. Now, when the magnetic field isn't changing, when the magnet is momentarily in rest, the electric field goes to 0. And when the magnet's moving, when the magnetic field is changing fast, the electric field is large. And when the magnetic field is changing slowly, the electric field is small. The little magenta arrow represents a vector minus dB dt, and we'll talk about how to calculate that. So it's the negative of the rate of change of the magnetic field across this surface. And you'll see that if you take your right hand and point your thumb in the direction of this magenta vector, your fingers curl around in the direction of the electric field that curls around in this curly pattern. Now, is this just motional EMF? We've got something moving. The answer is it's not motional EMF. It's actually different because we don't need to move anything to get this to happen. So we can get exactly the same effect by running a current through a coil. And so here on the left is a coil connected to a power supply. If we increase the current in the power supply, we see that the magnetic flux through that surface increases, and there was a curly electric field. If we now decrease the current in the power supply, we're still getting a curly field. If we run the current the other way, as long as the current is changing and therefore the magnetic field due to the coil is changing, we get this curly electric field. But if the current stops changing, the magnetic field stops changing, you don't get the curly electric field. So this is really different. It is it's a new thing. It looks like a time associated with a time varying magnetic field. There is in fact a curly electric field around the region where the time varying field exists. And it's a way that we hadn't known about to make an electric field. Furthermore, what the pattern of field we saw was actually a pretty unfamiliar pattern. It was a curly field. And you may recall that we had said earlier that, that we couldn't have a pattern of curly electric field. We'd said that if we glued down stationary point charges to make a pattern of electric field that looked like this, that would actually violate the fundamental idea that the round trip potential difference, the integral of minus integral of E dot dl was 0. So it looks like this is a really, really, really different phenomenon. And in fact, to distinguish it from the field made by charges, we call it a non-Coulomb electric field. It's not made directly by stationary charges. Now, does this violate conservation of energy? It doesn't, because we are having to put energy into the system to make this curly electric field. We either had to put energy in to move the magnet, or we had to put energy in to run the current in the coil and change the magnitude of the current in the coil and direction. So we were putting energy in. So it looks like it's possible for the integral of the round trip integral of some non-Coulomb electric field around a closed path to be non-zero. Now it didn't just depend on magnetic field, because a constant magnetic field doesn't do it. You may have noticed that when in the video, the guy, he moved the magnet into the coil and there was current, and then the needle went back to 0. Now there was still a large magnetic field inside that coil, but because it wasn't changing, you didn't get a current, and then pulled it out and we got the current again. So it's only when the magnetic field is varying in time that we get this electric field. And the reason he had the coil there was so we could see an effect of the field. So you could see it actually running a current in that coil. The electric field would be there in space even if the coil wasn't there to detect it. So if we put a proton there, it would be accelerated by this field and pick up space. The direction of this field is given by a slightly different right-hand rule. Where if we point our thumb in the direction of a minus dB dt, so opposite to the rate of change of v, then our fingers curl in the direction of this non-Coulomb electric field. Now, we say it's a non-Coulomb field because it's not made by stationary charges. But in fact, it does exactly the same thing as any other electric field does. It affects charges, it exerts these usual kind of forces. And we'll see in a minute that the magnitude depends on the rate of change of the magnetic flux through a surface bounded by this loop. So how do we figure out the direction of dB dt? So figuring out okay. The easy way to do it is to consider discrete positions. Or discrete times. So let's say at time t1 we have a magnetic field B1 in that direction. And at time t2 we find that we have a larger magnetic field in the same direction. To get the change in magnetic field, that's just going to be a B2 minus B1. And remember that to subtract vectors, we put them tail to tail. So what we would do is draw these vectors tail to tail. It's hard to subtract collinear vectors graphically because it's hard to draw them. You have to offset them slightly. So in this case, we would draw B1 and B2. We won't draw them quite on top of each other because that's hard to do. And then B2 minus B1 is sorry, B2 minus B1 is delta B, which is that way. So that's the change in B. Delta B is what we have to add to B2 to get to B1, right? B1 to get to B2. So B1 plus the change in B is equal to B2. So the vector subtraction goes from the first vector to the second vector. It's easier, of course, if we had non-collinear vectors. If we had a B1 and a B2, then that would be easier to see. What if the vectors were, what if magnetic field was changing the other way? So suppose we had a large magnetic field at time t1 and a smaller magnetic field at time t2. Then what we'd have to add to get to B1 to get B2 would be that vector delta B. And of course, delta B has a magnitude as well as a direction. So if we have two vectors here at time t1, B1 is equal to 0, negative 5 times 10 to the negative 4 0 Tesla. And at time t2, B2 is equal to 0. It's smaller in magnitude, so it's less negative. So negative 3 times 10 to the negative 4 Tesla. And say this is, this time is 3.01 seconds, and this is 3.05 seconds. Then delta B over delta T which is an approximation to dB dt, would just be B2 minus B1 over T2 minus T1. So that's a plus 2 times 10 to the negative 4 Tesla in the y direction over 0.04 seconds. So 4 times 10 to the negative 2 seconds. And so what we'd get is a 5 times 10 to the negative 5th 0 Tesla per second. And of course, minus delta B over delta T would just multiply that by a -1. So we'd have a -5 times 10 to the negative 5th 0 Tesla per second. Okay, so let's see if we can answer a question about this. Okay, so here's our question. We have a magnet with its north pole up that's located on the negative y-axis, and it's moving away from the origin. So at time t1, it's closer. At time t2, it's farther away. During this interval, what is the direction of negative delta B over delta T? Okay, think about this for a second and see if you can work it out. Okay, so I'm seeing 4s and negative y's, which are the same thing. So let's just check it. Okay, so it could have been plus y. So let's figure it out. So at time t1, we have a magnetic field that points away from the North Pole here. So at time t1, we have magnetic field B1. At time t2, the magnet is farther away. So the magnetic field is smaller. And so we have delta B, which is what we had to add to B1 to get to B2. So we have delta B in the negative y direction. So in fact, delta B over delta T, because the direction isn't going to change because our change in time is always going forward, so delta T is always a positive scalar. So delta B over delta T is going to be in the minus y direction, right? Do you agree with that? And so, but we were asked for minus delta B over delta T. And since delta B over delta T is in the minus y direction, it looks like minus delta B over delta T has to be in the plus y direction. So there's this extra step of multiplying by -1 once you get the answer. Now, why do we need to do that? Well, we need to do that so we can tell the direction of the Curly electric field that exists in this region due to this moving magnet. So let's see if we can actually draw it here. We have So at the origin, we have a, let's make it magenta, we have a negative delta B over delta T in the plus Y direction. And if we point our thumb in the plus Y direction, taking our right hand, put our thumb in the plus Y direction, then our fingers are going to curl around in the direction of the pattern of curly electric field here. So what does that imply for electric field in this region around the origin? So let's consider locations around the origin. It looks like we're getting a counterclockwise curl, which should mean that at this location we have an electric field in the minus Z direction. This is plus Z, and this is plus X, and this is plus Y. And so here on the Z axis, so this is going to be minus Z. Here on the Z axis, we'd get a plus X. Here on the negative X axis, we'd get a plus Z. And here on the negative Z axis, we'd be getting this minus X. Sometimes this is easier if we draw it so that dB dt is perpendicular to the page. So if we consider a solenoid, remember that in a solenoid, which is a really long, tightly wound coil, the magnetic field inside the solenoid is very large and extremely uniform. So if we have a solenoid in which the magnetic field is, say, out, and also remember that outside the solenoid, the magnetic field is nearly zero. So if the magnetic field inside the solenoid is out of the page and it's increasing, then let's think. At time T1, the magnetic field is out of the page toward us. At time T2, it's out of the page toward us, but larger. That means delta B was out of the page, so minus dB dt, or delta B over delta T, is into the page. And so if we point our thumb of our right hand into the page, our fingers are going to curl around clockwise, and that suggests a pattern of curly electric field in this region. Now note something interesting about this. In the case of the solenoid, there's a very large magnetic field inside the solenoid, but outside the solenoid, the magnetic field is nearly zero. And yet, because in this inner region, there is a time-varying magnetic field, anywhere outside of that loop, there is an curly electric field, even though the magnetic field at the location of our observation location here is actually zero, or very close to zero. So it's the magnetic, as long as inside this region somewhere there's a time-varying magnetic field, then outside of the region, that electric field will still be there. Will there be an electric field inside this region? Yes, absolutely. So in fact, we would definitely see a curly electric field inside here as well. Now, this can be useful because the electric field can drive a current. So if we put a loop of wire here, we'd get an electric field that could drive a current. And how big, what's the magnitude of E around this loop? Well, whatever the EMF is, that's equal to this integral of the non-Coulomb field around this loop. And that's just equal in this case, since the magnitude, we've drawn this, or I tried to draw it centered on the solenoid. This would just be the magnitude of E times the integral of dl, which gives us E times 2 pi r, the circumference of this loop here. So we can calculate the magnitude of the electric field, and therefore we could actually do, if we can get the EMF. So how does this all fit together quantitatively? So quantitatively, remember flux from Gauss's law. Okay, so we have magnetic flux is just the sum of B dot n hat delta A over some surface. Or if we want to write it so that it's always true, we can write it as an integral of B dot n hat dA. And that, of course, is the perpendicular is equal to the perpendicular component of B times the area element of this surface. Okay. So Faraday's law says that is expressed often in terms of EMF in some piece of wire or something. And it says that the EMF is equal to the minus negative rate of change of the magnetic flux, where this is EMF around a loop. And this is through the surface inside the loop. So it's as if you made a loop out of wire and then dipped it into a soap solution, and you came up with a nice soap film across this loop of wire. The EMF in this loop of wire would be proportional to the rate of change of magnetic flux through the soap film. And to be more general, we can write this as the integral of the non-Coulomb electric field times dl around a loop. And that's equal, and this is equal to minus d dt, the integral of B dot n hat dA over a bounded surface. So this is Faraday's law. The minus sign is mostly what we're going to do actually is get magnitude and direction separately. The minus sign is a way of getting the direction, which basically involves a right-hand rule. Now, we actually could write this as not just involving the non-Coulomb electric field, but we could write it involving, what was the written subscript to make? I'm not sure I understand your question, Flavio. It just says magnetic. Oh, that just says magnetic. Sorry. Now notice this is not a closed surface, it's a bounded surface. Now, what we saw in the video was not just one loop, but many, many, many loops. And so if you have many loops in a coil, the EMF, so say n loops in a coil, would really be n times minus the rate of change of magnetic flux through one loop. Okay, so it hasn't been all that long, but let's remind ourselves about magnetic flux. Let's see, this question. So here we have a rectangle, and we could draw our loop around the edges of the rectangle here. And the question is, what's the magnetic flux through this rectangle? So take a moment and think about it and make sure you think you know how to do it, and then we'll do it together. Okay, so some of you should actually have an answer by now. Remember that to do this, we need to have an n hat. So that's a vector normal to the surface. So that's going to be in the plus y direction here. So in this situation, n hat is going to be 0, 1, 0. So b dot n hat. Okay, so let's remember how we evaluated dot product. Is going to be 0.5, 0.20 Tesla dot 0.10. Remember that a dot product gives us a scalar, so it's 0.5 times 0 plus 0.2 times 1 plus 0 times 0. So that's just b dot n hat. And now b dot n hat times the area is going to be, so that just equals a 0.2 Tesla. It's going to be 0.2 Tesla times 3 meters times 2 meters. So that's 6 times 0.2 is going to give us a 1.2 Tesla meters squared. So the difference, so flux can be calculated to speak to your question, Patrick. Flux can be calculated on any surface. So it can be a flat surface. We can still get flux through that surface. The question is if that's what we need to apply a physical law. For Gauss's law, it turned out that the flux through one piece of a bounded surface didn't give us any information, and we had to take all the pieces of a closed surface. We had to add up the flux all over that closed surface. Faraday's law is different. It says that we're interested in the electric field along some closed path, and we want the flux through the surface enclosed by that path, even though that's a single flat surface. Okay, so let's actually try a real example of Faraday's law and see what we can get. So let's write it down here again. We have EMF is let's write magnitudes. The rate of change of let me make that clearer. The rate of change of magnetic flux. So let's consider a situation where we've got a magnet. Here's our north end. Moving along an axis where we've got a coil. That has 500 turns. And the radius of the coil is 3 centimeters. And at the instant shown, the magnetic field, this is time t1, the magnetic field B1 has a value of 0.2 Tesla. And at time t2, we just take the magnet and move it very far away. So B2 is approximately 0. And let's say we do this in a time of 0.3 of a second. So we hold the magnet here near the coil and we just jerk it away. Okay, let's calculate the EMF in this coil. Well, it's going to be, suppose we should put an N in this equation for the number of turns. So the EMF is going to be equal to, we have 500 turns. And now we want the change in magnetic flux over the chain, over delta T. Well, let's calculate the magnetic flux at time T1. So we have the flux in one, so the flux in one turn is going to be equal to approximately the magnetic field, which is 0.2 Tesla, times the area inside the coil, which is just a pi times 0.03 meters squared. And at time T2, the flux through one turn is 0. So it looks like it's going to be 500 times 0 minus whatever this comes out to, 0.2 Tesla times pi times 0.03 meters squared this whole thing divided by the time it took, which was 0.3 seconds. And if we work this out, we discover that we get something like 9.4 times 10 to the minus 2 volts, so 0.09 volts. Now, if circumstances were different, you'd be doing an experiment with this in lab. But unfortunately, that's not something we can manage because we don't have coils. And what would you need to actually see this? Well, you kind of need something like a recording voltmeter, because the voltmeter might say the number for a very short time, but of course it's actually going to be changing a little. So what we'd like to do is use a computer interface or a device called an oscilloscope, which these days is basically a computer interface, and it's just a recording voltmeter. It just gives you a graph of voltage versus time so that you could actually measure this. Now, presumably, we could actually calculate the electric field in this wire, because this is the integral of E dot dl, that's the EMF. And so that would be equal to whatever the magnitude of the field is times, well, the whole length of the entire coil. So the circumference of one coil, of one turn, times the number of turns. So it'd be 2 pi times 0.03 meters times 500. And so if that was 9.4 times 10 to the minus 2 volts, we could, this is circumference of one loop times n loops. So we can divide this by that and get the electric field, which will be small. So EMF is proportional to the rate of change of magnetic flux, right? So here we approximate, the exact expression involves a derivative. Here what we've done is approximated the derivative by a ratio of finite differences. So we took a delta B over a delta T, and we said, so we're saying that delta B over a delta T is our approximation to a dB dt here. Okay, so what would be the direction that conventional current would run in this coil during the time we're moving this magnet? So well, we need to go back to our right-hand rule. So we had B1 in that direction. We have B2 is 0. So delta B would be 0 minus B1. So delta B would be whatever we had to add to B1 to get B2. So delta B would be that direction. So a minus delta B over delta T is going to be in that direction. So if we point our thumb in the drawing up here, we point our thumb in the direction of minus delta B over delta T, which we see is in the same direction as the original magnetic field in this particular case, but it won't always be. We see that our fingers are going to curl clockwise around this coil so that the electric field in one turn of this coil looks like it would end up pointing this way. And so conventional current will be flowing clockwise through this coil during the time when that's happening. Okay, let's look at one other question just because it makes an interesting point here. So here we have a solenoid in which the magnetic flux changes inside the solenoid from, you're given two values of the flux, 6 times 10 to the minus 4 Tesla meters squared to 2.10 times to the minus 4 Tesla meters squared in a tenth of a second. The ring radius is 10 centimeters and the solenoid radius is 2 centimeters. So what's the EMF in this outer ring? Think about this for a minute. The interesting thing about this question is that if this is an ideal solenoid or even just a very good solenoid, the magnetic field outside here is nearly zero. And yet there really is an electric field, a curly electric field in this region, including at the location of this ring, due to the changing flux inside the solenoid. So to get the total flux through the ring, we would need to consider the area of the ring that's outside the solenoid. But since the magnetic flux is nearly zero here, then in fact, it's only the flux inside the solenoid that is going to matter. So to calculate this magnetic flux, which has been done for us here, this is going to be the magnetic field inside the ring. It's in the area of one turn of the solenoid. And then we're going to have to multiply by the number of turns. So to get the EMF here, all we would need to do is say that the EMF is equal to the rate of change of magnetic flux. And that's, again, we're going to approximate this derivative by a finite difference. So it would be 6 times 10 to the minus 4th Tesla meters squared minus 2 times 10 to the minus 4th Tesla meters squared divided by 0.1 seconds, which would give us 4 times 10 to the minus 3 volts. Now, what is the value of E in the outer ring? So Well, notice that we are, so the question is, shouldn't it be negative? Yes, this difference is indeed negative, but notice that we said we were going to take the absolute values up here. So let's do that. So we want the absolute absolute value of the EMF, and we're going to get we would get the direction by using the right-hand rule, since the magnetic field the magnetic flux is decreasing. It looks like we would have had B1, B2 would have been smaller. So delta B would have been to the left. So a minus delta B over delta T would be to the right, which gives us a current that's gonna, a conventional current that's gonna flow that way. So again, the sign in this, I mean, if we do this, there's a minus sign here, actually. If we do this, you can read about that in the book, but if you want to do it very formally, you can use the sign to get the direction. But in fact, the best way to get the direction is to use the right-hand rule with minus dB dt. So the magnitude of the electric field in the outer ring, we would just get, so since EMF is the integral of E dot dl, and we cleverly centered the ring on the solenoid so that we know that the magnitude of E is the same all the way around the ring. This would just be E times the integral of dl, which is E times 2 pi r, where this is the radius of the outer ring. So the electric field would be the EMF over 2 pi r, which is 4 times 10 to the minus third volts, divided by 2 pi times, what was the radius, 10 centimeters. Which gives us about 6.4 times 10 to the negative third volts per meter. Okay, questions about this? All right. In recitation, we will practice doing calculations and directions, which are important with Faraday's law.